Hi everyone and welcome back to chemistry. This is Mrs. Hutchinson again, and today we're going to switch gears a little bit and talk more about matter and change, and more explicitly the phases of matter. So hopefully this particular video happens to be a review for you, because my guess is that you probably have talked about solid, liquid, and gas phases of matter in other sciences. So let's get to it. So phases or states of matter, those terms can be used interchangeably, but basically the phase of matter that any particular substance is in is solely dependent upon how much energy that particular matter has. So the solid phase, they have the least amount of energy, and the way that we can tell that they have the least amount of energy would be because the molecules just simply shiver in place. What that means is, if you're just simply standing there, which you're more than welcome to stand up and actually act this out. So if you're standing, you just kind of sway side to side. That's really what these solid particles are actually doing. It doesn't take very much energy for you to do that, and it doesn't take very much energy for them to do that. So that's why we would say that the solid phase of matter has the least amount of energy. Now, the solid phase that I'm talking about would be something like ice, or table salt, or sugar. Okay. With that, we would state that each solid molecule, or each solid substance, has a definite shape and definite volume. Basically what I mean is, if you put an ice cube, and it's not going to melt, if you put an ice cube into a cup, that ice cube is not going to take the shape of the cup, but rather remain whatever shape the ice cube was the ice was frozen in. So that means that it has a definite shape. The definite volume means that, well, it's not altering its volume as it's going from one material to another. So if we take this particular picture, for instance, what this is we've got an outside box, and inside of it we've got a nice solid cube. If we transfer that cube to, say, a balloon, which can't draw a balloon, but that's the best I've got. So if we draw a balloon and we put that solid cube inside of this balloon, it's not taking the shape of the balloon, but rather it's still a solid cube. That's what we mean by it having a definite shape and definite volume. It's not taking up any more volume inside the balloon here than it is taking up inside of our square container. Regular geometric pattern, what that basically means is that the substances at the molecular level are oriented in such a way that it makes a nice geometric shape. So if you want to think about table salt, for example, these are, say, particles of table salt. I blew them up to exorbitant proportions, and they're actually physically combined. The elements of table salt, Na and Cl, are physically combined in a cubic shape. So a regular cube. Pew, 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 pew. Just like that. Okay? If you look at a single piece of salt, just one, you sprinkle a salt shaker right on the table and take a look at one piece of salt. It's not like they have a machine that's going to cut each piece of salt in a cubic fashion. But the molecules themselves, the particles themselves that make up table salt, sodium and chloride, will arrange themselves in that cubic shape, which is kind of cool. And pretty much, if you observe things, you'll find that a lot of substances do that. So taking a look at the solid phase at the molecular level, we're going to represent each particle, or each element, or atom, by a dot here, and you'll notice that they're all tightly packed together, because they're in the solid phase. They're not free-flowing, they're just vibrating, moving back and forth. And we also notice that the solid is found at the bottom of the container. The reason why it's found at the bottom of the container is that all solids, when they're just in a container filled with air, are not going to float at the top. They're going to rest at the bottom. Much like your ice cube, or if you put sugar in a glass, or salt in a glass, or something like pills in a glass. I don't know why you would have pills in a glass, but you could. So things you want to really think about when you're creating a structure or a picture of what a solid might look like, make sure you put it at the bottom. Okay. Next one, the liquid phase. Also, side note, I got these pictures from NASA, so if you want to take a look at NASA's website, you can see them. They're pretty, I'm there all the time, but that's just me. So, we say that liquid, in terms of energy, it's going to have more energy than a solid, but less than a gas. So, remember our solids, you were just kind of standing and swaying? Things you want to think about for liquids is now you're suddenly you're suddenly walking around. And when I say walking, I mean more of like a sauntering. So you were swaying, now you're just kind of sauntering, walking kind of slowly. But that walking takes more energy, more effort than it does to simply sway. That's why the liquid phase has more energy in its particles than it does in a solid. Another way to think about it is, well, the particles or molecules, they just kind of flow. When you're walking, you're just kind of flowing around. Molecules in the liquid phase will move faster than those in the solid phase because they have more energy, but slower than those in the gaseous phase because they have less energy. So things we want to really think about when looking at liquids. Liquids take the shape of their container. Here's what I mean by that. If we have my graduated cylinder that, if you haven't noticed, I'm a horrendous drawer, which is absolutely fine. I own up to it. I know it. So you feel free to make fun of it. That it is definitely an area where I need to work on. So if we take a look at my horrendous graduated cylinder here, and let's just say we have 100 milliliters of water in that graduated cylinder. If we take that 100 milliliters of water and we pour it into this square glass container, we still have 100 milliliters of water, but now the shape that the water has taken is different. So here's what we mean by that. We have a definite volume. Our definite volume would be 100 milliliters because in either container, that liquid will measure out to be exactly 100 milliliters. But no definite shape, meaning our liquid is going to take the shape of whatever container it is in, whether it's your water bottle, your graduated cylinder, your square container, your beaker, anything like that. So liquids always take the shape of its container. And if we draw what the liquid is going to look like at the molecular level, things you want to think about. Liquids, they don't float on gas, at least not normally. So if each one of these dots represents a liquid particle, we notice that the liquids are a little more spaced out, not quite as regular, but they're found at the bottom of the container. Because in your water bottle, where is the liquid found? It's found at the bottom of the water bottle. It's not like you have air at the bottom and water on the top. As cool as that may be, we have air on the top and water on the bottom. So our liquids are going to be found on the bottom of whatever container we are looking at. If we then move to gases, gases, they have the most amount of energy. So we started off swaying as our solid, and then we started to kind of saunter as our liquid, and now think about you have a sudden burst of energy as a gas. More explicitly, let's really make this kind of fun, but don't do it. It's not really the safest thing. But think about this. You're in a padded room, because who wouldn't want to be? You're blindfolded, because who wouldn't want to be? And you are told to sprint as fast as you can. You are going to be running in straight, random motion. That's exactly what gas particles do. So you're running around in this padded room, running into walls, running into people. And it takes the most amount of energy because you are running. You're not just sauntering, you're not just swaying. That's what these gas particles are doing. We would also state that the gas particles have no definite shape and no definite volume. What we mean by that is if we take a look at all the gas particles that are in here, we can compress them by increasing the pressure and we can put them into a smaller container. So we can lessen the distances between the gas particles. Therefore, it has no definite volume. If we lessen those distances, we're taking up less volume. No definite shape means that it's going to now take the shape of its container, much like it did for our liquid. So as you're drinking your water bottle, it's not like you have nothing at the top of that water bottle. That water bottle is now filling with a gas, which we call air. So the major difference between the gas phase and the liquid phase would be that our gas particles, instead of our liquid particles being at the bottom, our gas particles are going to take the shape of the entire container itself. And it does not have to be as organized as I made that. Okay, so our gas particles are going to take the entire shape of the container. So now, what I want you to do is take a look at your Phases of Matter worksheet, read through the depiction or description, and figure out what phase of matter we're talking about. So, for example, table salt has a regular geometric pattern which gives it its trademark cube shape. A regular geometric pattern is associated with a solid. Therefore, we're talking about the solid phase. So go through this worksheet and just identify what phase of matter we're looking at. And once you're done, I'll see you at the next video.